We're going to keep going on vectors, 2D kinematics, and trajectories today. So before we get started, let's talk about Canvas. I think Canvas went pretty well. No major problems. I know a lot of you, people stopped coming. Oh my God. I know a lot of you, it marked you late even though you turned it in on Monday. So I don't know what that's about, but we will give you your credit back, don't worry. And we'll try to figure out why Canvas is doing that. It just randomly picks you and randomly picks problems and says, this is late. Okay, so it's just Canvas being stupid. But believe it or not, I am smarter than Canvas, and I can fix those grades, okay? I'm not dumber than Canvas. So last time we talked about vectors. We spent a huge amount of time on vectors. So hopefully that was just to get the ideas in your head. When you do the problems, you'll become an expert with vectors. We talked about the notation, and I told you the secret that what you're really struggling with in vectors is transferring between two coordinate systems, polar and Cartesian, polar bear and rainy day Cartesian. And we talked a little bit about how to add and subtract and multiply by a constant, and maybe the adding gave you some insight into why we use the unit vectors. Remember the unit vectors? So hopefully that all helped. And we'll do a lot more today of identifying them in kinematics problems, because as you know, we moved on to kinematics. Okay, so we're describing how things move in 2 dimensions now. You throw something up in the air and it's accelerating down due to gravity the whole time, but it may be moving this way. And for now, those two things are separate. So the one problem that we worked on last time in detail was the shoot and the drop. Remember, we did shoot and drop. One thing shot this way, one just dropped this way, and they took the same time to get to the bottom. So I derived it and did my standard thing, and we found it takes the square root of 2h over g to get there. And then somebody asked a very good question at the end that illustrates what you have to do in a problem, the hard part of a problem. Remember, is all context, right? Somebody asked, well, why did you know to deal with the y? Remember that we had the y equation and we had the x equations. And what do we focus on the y and not the x? So the answer is you have to look at the problem. What were you asked? Right? That's the question. What were you asked in shoot and drop? One is going to fall this way, one is going to go like that. And the question was, will they hit at the same time? So which direction is going to determine if they hit at the same time? So hit meant hit the ground. They're up high and they go low. So it's got to be, the question is leading you to think about the y. If the question had been, how far does this one go in the time it takes this one to hit the ground? Then how far, you would think, oh, that means the x. Right? But the question was only about how long does it take to drop. Right? Drop means down. So you draw it and you say, they mean down. In a Cartesian coordinate system, that's what we've been calling the y. So that's how I knew. It's from reading the problem and getting context. They will often, a problem will not say, calculate the velocity in the y after t.2 seconds. We know you can do that. You just plug it into the formula. So the problems have these kind of questions that rely on a little bit of context. So think of them that way. Okay, so let's see. The first thing then we're going to do is, so we're going to consider shoot and drop done and solved. And that was basically an example of sort of doing this, but we didn't really call it a projectile. What we're going to do now is really look at the properties of projectile motion. Projectile motion. So I'm just going to say the definition of these problems is that you launch at theta above the horizontal. That's usually the angle they give you. How high do you launch a projectile? At speed v naught. I'm going to call it v naught. And I'm going to put the bars and do the full formal mathematical notation. Remember, all this notation means is you're given an initial velocity. The velocity is a vector, but they're just going to tell you the magnitude. And they are giving you an angle and a speed or a magnitude. So what coordinates are they giving you? Polar bear coordinates, right? You begin this problem in polar bear. So what we're going to do is think about it. So what it looks like, of course, we can get the gun back out. This is Texas after all, so we use guns to illustrate everything. So what it means is we're going to give the bullet an initial velocity at some angle, and it makes a trajectory kind of like that, right? Late? No. Never be late to this. Okay. And if I give it a lower angle, right, it goes kind of a low trajectory like that. If I give it a high angle, up and down like that, all right? So that's what we're going to think about. And you can answer fun questions like, what angle will it go the farthest, etc., etc., etc. Okay, so let's draw it. First thing we do is draw it like this. So here's the ground. Here I am. Let's see. So we're going to give the projectile an initial velocity v naught. So one trick about notation and books and what we write is you can be real formal and write the vector with the hat on it and put the two bars that means magnitude. Or you can also just write it and leave the vector hat off. That's a quicker way to mean magnitude, right? The bars and the arrow hat, it's a little bit cleaner. So if I write it without all that on it, I mean just the magnitude. Because it's a vector because I gave you the angle theta there. Right? So we got v naught and theta. And technically, we should say that this is theta naught. Right? Because as the thing goes through this trajectory, the angle theta is going to change. Really, if you think about it, it's going to go up and down and positive and negative. And that's something you'll have to calculate. Then it's going to fly up, and I'll draw the parabolic trajectory. And if you're really with it, you know that the parabolic trajectory has to follow below that vector. But if you draw it wrong, that's okay. So it goes something like that. And let's pick a point. Let's pick the peak here. I should have drawn this bigger, so get out your opera glasses here. Let's pick the peak, and let's draw some vectors to practice identifying vectors in kinematics problems. Okay, so I told you last time, velocity vector you can draw anywhere you want. So the velocity here, maybe you can intuit that it's this way. Because remember, velocity is always along the trajectory, right? It's tangent to the trajectory. So this would be the v. I'll put a vector hat on it because it's a vector now, and not v naught because v naught's the initial, right? This is how it's moving later. Could put the acceleration on it, right? Acceleration is down because it's a free thing moving near the Earth. So there's a. We know it's down 9.8 meters per second squared. And the maybe trickier one is I could put the position vector on it. Right? Position, we can't just draw wherever we want because it's always implied in your drawing that this is an xy coordinate system. Right? Here's y, here's x, because you're drawing in the real world. This isn't some art class where you have like a color space and velocity directions. No. This is a real world drawing. Here's x, here's y. Therefore, this is the origin. Therefore, r at that point looks like this. Okay? That's the only one you have to draw right there. So as it goes through the trajectory, v kind of aims with the path, a is down the whole time, and r is from the origin to the path the whole time. So in some other video class, they can make a video of it. Okay? So what we want to calculate, the three main things you calculate for a projectile is how far does it go? That's the military part. And then how long is it in the air? Right, that's the whatever, physics, homework part. And of course, how high does it go? So we're going to drive those three just for practice, thinking about kinematics. And they're sort of equations that you're going to need, maybe even on the MCAT. I would say you don't derive, or you don't memorize them. I'd say derive them every time. Because you're going to see they're a little bit, there's three, and they're almost the same. So they're really hard to distinguish in your head. And I know y'all are bioscience and good at memorizing things, but still. Let's be sure you follow the derivation. So in a pinch, you could derive them if you needed to. Okay, so let's see. We're going to say the hang time is one of these. So sports analogy, I apologize. Hang time is the time in the air. And it's set by... What do you think it's set by? Think about it in your head for a second. We'll see if you're right. It's set by the y motion. Right? How long it's in the air, we're going to look at y. And it basically depends on what your initial velocity y component and what's your acceleration coming down. And that's how long it's in the air. Right? So it's set by y. All right. Let's look at this. We're going to do it a little bit quickie version here. Let's look at it. Let's look at just the up. Let's calculate t up. Okay, how long does it take it to get from here to here? Because if you look at that and think about what you've got and what you need and what you know, there's a quick way to do that. You know it has an initial velocity, v naught, which component? Let's see, v naught is vx plus vy. It's this side, sine theta. Right? V initial is v naught sine theta. You also know it's sine theta because of v initial y, I'll say viy. You also know it's sine theta because this is the standard definition of theta, right? It's counterclockwise from the horizontal axis. So instead of having to think about SOHCAHTOA, you could also just use the standard formula because it's following the standard rules. Okay? I am determined to see my text this time, but oh my God, here we go. Just a couple. What is r? R is the position vector. Theta for the position vector r is different than theta for the initial velocity vector r. Yeah, there's thetas all over the place. The only theta we've defined so far is theta naught. We will define them as we go. La la la. There's one more right there. I'm not used to calling that theta naught. Okay, so we have the initial velocity up is v naught sine theta naught. So all we got to think about is how it's going to evolve in time. So constant acceleration kinematics, remember that v final equals v initial plus acceleration times time. So that's what we're going to use. Because we're trying to find the time. We know the acceleration, we know vi, but we don't know vf. Oh yeah, we do. It stops. Right? We're trying to find the halfway. So one thing, you can do everything purely by kinematics, but if you kind of realize a uniform trajectory is kind of symmetric, it's a lot easier. Okay, so a uniform trajectory, it starts at v naught, starts at theta naught, it goes through this symmetric parabolic path, and it lands with an angle that's kind of down at the same angle. It's got the same x component and just a negative y component. If it's a uniform trajectory, that means it started and ended at the same height. Okay? We'll do uneven trajectories later. This is even. Okay? See, uneven is a harder thing we're going to do in a little bit. Okay, so this is on the way up. So we say Vf final equals V initial is V naught sine theta naught. That's that component. Plus the acceleration times time. So to help with negative signs, I'm going to start writing like this. Plus the acceleration is negative 9.8. Okay? A is equal to negative and then the number g. Because we define positive as up, acceleration is down. So we put in negative 9.8 t. Like that. This is not a numerical one, right? Yeah. Okay. So we solve for that, and that's not the hang time yet, that's t up. So t up is, this comes over here and becomes positive, and I'm actually going to go back to calling this g. I forgot we're doing a symbolic problem here. V naught sine theta naught over g. All right. That's how long it takes to go up. And now, t down. There's two ways you could get the time down. You could say, well, I'm dropping something from this height. I don't know what that height is yet. So you go solve for the height. And then you figure out the time down. Or you can just say, Hafner said it's symmetric, so it's the same. Right? So for now, just trust me. I don't want to do the kinematics like 5 times, because we're going to get the height another way. Okay? So I would say, just say same. Because I'm promising you, if you launch something, v naught, theta naught, and you ask when it hits the same height, and it just has acceleration down, the time to here will be the same as the time to here. The Vx will be constant. The Vy will switch. It all kind of makes sense that way. So think about it symmetrically. You have to get used to thinking symmetrically. So t down is the same. Therefore, t hang is just 2 times that. Right? 2 v naught sine theta naught over g. And the only way that will be different from what you might see in other books is they won't put theta naught. There'll only be one theta in the problem. But this being where it is, we will, of course, ask you other thetas, okay? Just to make life difficult, right? How did you get from 0 v sine theta to negative t to t up? So where did this come from? This is just a standard kinematics equation, and v final is 0. When it's at the top, what's its y velocity? 0. Look, here's its velocity vector. It's all x component. It's no y component. So that's 0, that's v initial, and that's minus 9.8 t. Okay. So that is the hang time, right? So any projectile, you could calculate the hang time if you pretend that there's no air resistance and blah, 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 blah. Now let's look at the range. Let's see. The range is how far it goes. How far is it going to get? Well, once you have the hang time, this one isn't so bad. Right, so for the hang time, for the range, first of all, what dimension do we care about for the range? How far it gets is x. So it's probably going to be an x kinematics problem. So you could say, oh, I know all x kinematics have to follow this, plus vixt plus 1/2 axt squared. If you want a position, it's probably this equation. Okay, is it accelerating in the x? No, there's no gravity in the x, so this term's 0. So it's really uniform motion. And that's the equation for uniform motion, right? This is d equals vt. If this is the origin, whoops, I don't know. If that's the origin, what is x initial? 0, right? So that's 0. We don't need that. So we see all we got to really do is multiply the x component of the velocity times the time, the hang time, right? It's moving at the same x component the whole time it's in the air for the whole hang time. So really then the range is x final equals, what was the x component? It's v naught cosine theta, right? So here, this is v naught cosine theta naught. And then t was 2 v naught sine theta naught over g. 2 v naught sine theta naught over g. Right? What is this talking about? Okay. So now we just combine those. I want to get this wrong. Yes, of course. Then you combine these to get the range. So x final is the range because we started at 0. So you can call it big R if you want. Is 2 v naught squared sine theta naught cosine theta naught all over g. And that's the one you use to figure out how far it's going to go. Okay. Yes, there will be a formula sheet on the R exam. So you don't have to memorize these. You could memorize them, though, because there's no formula sheet on the MCAT. But you can see they all look similar. They're hard to memorize. You may also see this simpler because they use an identity to turn this into sine 2 theta, I think. There's some identity, sine times cosine is sine 2x or something. I don't memorize identities. Okay. And then the third one is the height. How high did it get? Here we go. Right, how high? Height. So you're reading a problem, and it says get the height. And you say, let's see, is that x kinematics or y kinematics? As y kinematics, right? And here we're using the formula acceleration for a distance. That is the kinematics formula that we derive from the other two. Remember, the standard one's this one is a good one when you have acceleration for a time. And this is a good one when you have acceleration for a time. If you have acceleration for a distance, we showed you if you combine two of them, you can get this other one, the famous Vf squared equals V initial squared plus 2a times delta x, or delta y, or we'll just call it d. Right. In this case, it'll be a delta y because it's height. And we can do that because we're asked, what's the distance? How high did it get? Well, we know what's going to happen. It's going to go from its initial Vy naught to 0 equals 2 times we know the acceleration, and then we know how high it's going to get. Okay. So final is 0. Right. When it goes to the top, that's 0. V initial, in this case, is Viy, which we already know is V naught sine theta naught, but it's squared. V naught squared sine squared theta naught. Right. Plus 2, negative 9.8 is the acceleration. And then d is really the height we're looking for. Right? It's d, the displacement, it's y minus y naught, but y naught is 0. So it's really just, it's the height. I'll put yh. How high did it get? Okay. Where did you get cosine from in the range equation? The cosine is the x component. Vix is v naught cosine theta naught. So if this is the v naught vector, the x component is the adjacent over the hypotenuse. So that's v naught x cosine theta. Oh my goodness. Stop talking about the MCAT, please. Okay. I took it this summer, the physics part. Why do we ignore the y component? This is a good question. It's an excellent question. Why do we ignore the y component when finding the range? Doesn't gravity affect how far it goes until it lands? Okay? So I am oversimplifying how you do these. I'm saying, we're getting the range. Only think about the x component. Okay, that's not really completely true. You write a kinematics equation for the x component, but you may be plugging things in that you got from the y component. So it is true that the two motions depend on each other. We have to use information from one to solve the problem for the other. I'm just saying to know how to get started, what equation do I even write down? It'd be an x equation. But you're right, the y depended on or I'm sorry, the time depended on the y motion. So you're correct. Yes, I think I'm more or less caught up here. Okay. We just got to finish this now. So bring this over here. That's negative over there. Turn it around. What do we get? I don't know. Let's see. I'll just read it off my notes. No, let me do the algebra. Let's see. The height, YH, is V naught squared sine squared theta naught over 2G. I think I can do that without my notes. All right. So there's the range for the height. I'm sorry. 2G. So those are the three sort of basic fundamental equations for an even trajectory. A uniform, starts at one height, ends at the same height. Okay? Those are the equations. So we might give you, I think the homework has a problem on that, a uniform trajectory. But of course we'll give you uneven trajectories because it's more challenging and you got to really understand it better. Okay? Let's see how we're doing, 4750. Okay, so that's what we're going to do first. So now we've talked about then height, hang time, range. You have the concept, you have the formula. What more could you want? Now let's do these two hard kind of problems, uneven trajectories and angles. Yeah, let's do that. So I was trying to think of an uneven trajectory that you're familiar with. And I remember there's some game, I don't know what the point of this game is, where you're like throwing a ping pong ball into a cup. What is it like that? I'm really bad at this game, and I'm also a fairly successful person. So if there's a correlation there, that's kind of up to you guys to figure out. Okay, whatever. I suck at this game. Okay. So what we're going to do is we're going to do a quick practice problem based on this game. Okay. Which no one plays under the age of 21 unless it's water pong, is my understanding of the system here. Uneven trajectory. Oh, this horrible shadow. Uneven trajectory problem. So this is this thing right here, uneven. This is why I wrote it down. Uneven trajectory. So what we're going to say is I'm going to throw these are made up numbers. I don't think they're accurate. I'm going to throw the ball at 3 meters per second at 60 degrees above the horizontal into a cup, and then where to put it. So how far away should it be? Okay, so there you go. There's an example of thinking. Now, what are they asking us to solve for? I wrote where to put it because I don't have a lot of room and time to write a nice sentence. But normally it'd say, how far away should you be from the cup? So you're thinking about like the x direction, right? But you're definitely going to have to rely on x and y. Somebody asked why this is positive. It's because I brought it to the other side. Okay, so let me draw it real quick. Here we go. This is like the table, and here's me, and I'm releasing the ball from here, right? And the cup is over here. So suddenly we see why this is an uneven trajectory, right? I'm releasing from here, and I'm landing here, and there's a difference between the two. So let's say, since we're doing this with numbers, there's a 0.4 meter difference, 40 centimeters from the height I release it to the height of the cup, 40 centimeters. And I released it, theta was 60 degrees, and then 3 meters per second, etc. Okay. So one way to do this, what I want to show you, is you could do it with full kinematics. You could just brute force solve this with kinematics by just writing the kinematics equations and solving them. Often you'll end up with having to solve a polynomial in time. You'll have like at squared plus bt plus c equals 0. And you can't factor it, and you'll have to use, what's that thing called? Theorem, where you have negative b plus or minus squared of b squared minus 4a over 2, whatever it is. Whatever that thing is. It's in your calculator. So you don't want to do that, or you could. There's nothing wrong with that. But you could also break this into a two-part problem and say, I'm going to think of the even trajectory that occurs here, and then that's just an initial value problem to get into there. Right? You could do that. That actually makes it a little bit easier. Since it breaks it up, the math comes out a little nicer. All right? So let's just do it that way real quick. Let's say, first of all then, for the even part, I'll call this the even range. Right? And now it's just plug and chug. Now it's easy. R, because since we derived all the equations, R is 2 times 3 squared times the sine of 60 times the cosine of 60 over 9.8. right? So we get 0.795 meters. So that's not the answer. That's not how far you need to be. That's to here. Okay? But now what we want to do is say, if it ends there, what velocity components does it have? What's it doing? And what's going to make it land here? Okay, I kind of drew it too far away. And then, how far is it from here to here? That's really the answer we're looking for, right? So what is the motion at x equals r? That's really the question. When it's right here, we know where it is now. We know how high it is, so we need to drop 40 centimeters. We know where the origin is for this second part. But what's the motion? How fast is it going? All right? So Vx naught, let's see, Vx naught didn't change, right? In one of these things, it doesn't change. The gravity is down. The x component is the same. Even after it ends the even trajectory and becomes an uneven trajectory, it's still going down. So we would say you just plug in the numbers, and it's, it's 3 times the cosine of 60. It's 1.5 meters per second. That's the x component. Right? And then what about y? Vy naught, this is for the second part now. This is here, right? So it's got a velocity component that way and a velocity component that way. Vx naught now, Vy naught here. So Vy naught is where, if you just believe me that it's symmetric, you don't have to do a bunch more equations, right? You just say, well, I know it's going to be the opposite that it was here. If it goes through an even symmetric trajectory, this one basically flips over. Whatever velocity it had to get up to that height is the same velocity it'll pick up when it falls back down. Okay? So you could just say then it's negative, and then just say 3 times the sine of 60, which is negative 2.6 meters per second. Okay? So now you're in pretty good shape, right? You have an object, you need it to fall 0.4 meters, and you know exactly how fast it's going. It seems like you're in good shape. So you need it to accelerate for a distance, don't you? You have a distance. It's going to accelerate. So the formula is the good old accelerate for a distance formula. Accelerate for a distance. Right? We're not asking you for a time. We're thinking about this distance to go like that. So we're going to use accel for distance. Okay, that's tricky to remember to do. Here in my notes, I started to do acceleration for a time, right? See, I even made the mistake. And then I didn't even cross it out. Okay. Where'd you get 0.4 meters? Yeah, I didn't say it in the problem. The cup, the distance between where my hand was and the top of the cup was 0.4 meters. I didn't write it as a sentence. Okay, acceleration for a distance. V final, how fast it's going here, we don't know, right? So that's what we're looking for. How fast does it get up to? V initial, we know, is negative 2.6 squared plus 2 times 9.8, negative 9.8 times d 0.4. Like that. See there. And you square that, it becomes positive. So you bring this one over, and everything remains positive. It's okay. And, oh, no, I'm sorry. This one becomes positive. This one's negative. You add them together to get the final velocity. And it does come out negative because it's down. And you get negative 3.82 meters per second. Right? V final y. Okay? So we just did that to find out once it drops, how fast is it going in y now? It's going faster in y. It's still got the same Vx naught. Okay? And why do we do that? Because we need to know, why aren't the lights on? The reason we did that is now we need to know how long does it take to go from here to here. Right? So that's, it fell, so how long is this second part? Well, our final was 3.82. V final minus 3.82 equals our initial was minus 2.6. Minus 2.6 plus acceleration 9.8 t. We got this final velocity because that'll help us figure out how long it's in the air for this little part. All right? And if you plug that in, you get 0.125 seconds. T, I'm just going to call it 0.125 seconds. You've got to be able to follow the notes. If I start making up infinite subscripts, it'll just be confusing. So this was the even, and this is the uneven part. Or this is like the extra part. So 0.125 seconds. Why do we get 0.125 seconds? Because we're trying to figure out how far it goes this way, right? So now we know. Now we know it flew in the x for 0.125 seconds. So the delta x is the vx that it's going 1.5 meters per second. 1.5 meters per second times 0.125 seconds. And is that the answer? No. That's how far it went right here. That's this part, right? And that is, if you work out the numbers later, 0.188 meters. All right? So this is 0.188 meters. Okay? And when you add them together, that's when you get the full answer, 0.983 meters. So you need that cup to be 0.983 meters. Okay? I just did that problem in like 8 minutes. Okay? I do not expect you to be able to do that problem in 8 minutes. If you were given that problem in your homework, like 2 hours maybe, well, some coffee breaks, go get some boba, cry a little bit, and then you might get it done. I just did it in 7 minutes. Not to show off, because we don't have 2 hours of class time. So if you were like desperately trying, you couldn't really follow it that fast, that's okay, right? You shouldn't be able to do it this fast. But this is the only way I can do problems in class. Okay, so when I burn through a problem in class really fast, I'm just trying to show you the tricks and how to think about it. I'm not expecting you to be able to do it that fast. Okay, so the tricks were, oh my God, it's an uneven trajectory. Let me do the even part first. I did the even part. Now I have the initial conditions for the little extra part, the little drop. And then it was actually pretty tricky. You got to get the velocity to be able to get the time to be able to get the distance. That's hard, right? But now you could do any uneven trajectory because they're all basically the same. Okay, let's see. Oh my God. Oh, no, that's perfect. No, it kind of sucks. Let's see. Okay, let me show you. Let's do all the hard stuff now. We'll do the fun stuff in the second half. So here's another one that would take you 2 hours and emails and going to help and all that. And I think I'll not do it in the mathematical detail I was going to do it in, but I'll tell you how to do this because you need to know how to do it. Here is another thing, angles, right? So here, the whole time we were doing the theta naught, this initial angle, but the angle changes as something flies, right? So let's see, let's say how to find the angle of a path. Very important. So I had a numerical version. What I'll do is I'll give you the numbers and you can later see if you can get the numbers to work out. Something flies at 5 meters per second. All right, at 45 degrees. So the trajectory does something like this, like that. The time, I'll just tell you, you could plug and chug and get the time, is 0.72 seconds. It's only in the air for just a second. Those bullets were in the air a long time because the air was slowing them down. Most of these aren't that long. Yeah, so then the question is, what is the angle at, I think I did t, I just drew a b, what was I thinking? At t equals 0.45 seconds. So t equals 0.72, what is this t? Somebody shout out what the time is when that happens. 0.36, good. You either don't know or you can't shout. Okay. Or both. Okay, yes, you're right. So since this is symmetric, half the time goes up, half the time goes down. This is 0.36 seconds. Right? This was 0.72 seconds. Right? So in this problem I said, find the angle at 0.45. I was just trying to find a place around here. Right? What is the angle of the trajectory at 0.45 seconds? That's the question. Okay, so here's what you do. We won't do the math, but I'll tell you what you do. You need an angle, probably related to a vector. Right? Let's identify some vectors. Is the angle of the trajectory this? No, that's not what we mean. You could argue that is the angle of the trajectory because the particle's on that trajectory and that's the angle of r. So you could say this is what you want. Well, you can say that if you want, but I wrote the problem and we wrote the answer. So that's not what we want. When we say the angle of a trajectory, we mean tangent to the trajectory. Okay? So which vector is going to give you that? V. Right? So how to find the angle of a path is it's the angle of V at t equals 0.45 seconds. So you got to do in this problem is figure out what are the components of V there. It's actually an uneven trajectory problem, really. You can use the even formulas to get the top, and then you got to figure out what it's doing at this point. Although you really don't have to always break it into two parts. So you'll find out how you could also do it with just one set of equations as we do more, as we go forward. But ultimately, how do you get an angle is you got to realize, okay, this V has two components. It has a component this way, it has a component this way. Right? This is the x component that never changed, and this is the y component that's going positive and then negative. So if your V looks like this, and you have Vx, and you have Vy, that's the angle right there, and it is the tangent of that angle is Vy over Vx, if you're following the standard definition. Okay? So when we solve this problem, and I'll give you the answer, what we would get is a negative number here, right? Because Vy is down. So that's a negative component of the velocity vector. We get a positive number here because Vx is to the right. So we get the tangent of a negative number, and the inverse tangent of a negative number is a negative angle. So the answer is minus 13.9 degrees. Okay. And that's that's right. It's negative 13.9 degrees. So if you want to go through the kinematics later and see if you can solve that one, it'd be a good practice. Okay. All right, so we're now going to do the most famous demonstration in all of physics because we've now done all the hard stuff, right? So now we did all this, even something we got to go back and do the hunter and the monkey. Just in case some of you don't believe that x and y motion is uncoupled, we're going to prove it with this famous demo that everybody has to see once. Let's see. I've seen it many times. Okay, so the idea of this is you have, and it's also just a good practice problem for us to do, is you're on the ground here, you have a hunter with a gun, all right? And he's got a gun, and the gun is going to shoot a bullet at V naught, and the angle is theta. And he's trying to shoot a monkey. Oh, why? Why? You can't eat a monkey. That doesn't make it okay, right? So a tree and a branch, and the monkey's hanging. Oh, shit, okay, and there's the legs right there. There's a monkey, right? So the question is, the hunter shoots, right? And the sound scares the monkey, right? So bang, and the monkey drops. Oh, no. Okay, so the question is, where should the hunter aim? Should the hunter aim right at the monkey? Should the hunter aim below the monkey because the monkey drops? What should the hunter do? So the hunter has seen this demonstration before, so let's say he's going to guess that he should aim right at the monkey, D. Okay? And he knows that the monkey is at a height h. So if he aims right at the monkey, shoots his gun at theta and V naught, does he hit the monkey? That's the question. And will we hit the monkey? That's the more important question. Okay? So what you would want to do is ask yourself, how much are each of these things going to fall? Okay? So let's first look at the time for the bullet to get from here to here. Time for bullet to cross D. Okay, so you look at that and say, which kinematics am I going to use? Am I going to use x or y? So it's to cross D. D is along the x, so we're going to use x. All right, so then you could say, well, okay, so if I'm going to use x, I'm probably going to use this. X final equals x initial plus v initial xt plus 1/2 ax t squared. All right, and you're going to say, oh, wait a minute. Do we have any acceleration in x? No. This is uniform motion. All right? And we're going to say initially we'll call this the origin. Drop it like it's not there. And final, what is x final then? X final is d. So d is there. So d is the initial x velocity, which is what? V naught cosine theta. D equals V naught cosine theta times t. Right? So the time for the bullet to cross D is just D over V naught cosine theta. Right? So that first time is D over V naught cosine theta naught. I guess we should be saying theta naught. Okay? Now I'm not going to give it a special subscript. You got to get used to this idea in these problems. We find this time. Okay, now we're going to go find this time. And now we find this height. You can be real careful writing subscripts every time, but it often will just throw you off. Okay? So we want to know is, when this follows this actual trajectory, are they going to be at the same place at the same time? That's another big word we use in kinematics problems is, do they hit? Right? Do they hit? So if they hit, then what that really is asking is y of the bullet equal y of the monkey at this time? Because we know at this time, x of the bullet equals x of the monkey. Right? That's what we just calculated. The monkey is always at d, and we just figured out when does the bullet get to d. So what we've got to do is take this time where the bullet's at d and plug it into their two y equations and just see what we get. All right? So let's first do y. Okay, so now we're answering the question, do they hit? Okay, so y, let's do the bullet first. Well, let's see. It's y final equals y initial plus vy initial t plus 1/2 at squared. So the final is the y of the bullet we're looking for. Initial is 0. I won't even write it, right? It started from the ground. Plus vy initial, which was v naught sine theta. V naught sine theta. And then the t that we just did, d over v naught cosine theta. D over v naught cosine theta naught. Okay, so that is vy I t. And then minus 1/2, or plus 1/2, negative 9, well, whatever, negative 9.8. And then this same t squared. Oh my God, d squared over v naught squared cosine squared. D squared over v naught squared cosine squared theta naught. That's where it'll be in y. Let's see, this is negative though, sorry. I kept jumping. Oh no, I put the negative there. I'm trying to do that to help you remember. Okay? That's y of the bullet. Okay? Initial y velocity, it's decelerating down, no initial position, and we plugged in a specific time. Right? The time is in there. There it is, d over v naught cosine theta, d squared over v naught squared cosine squared to the third. Y of the monkey is simpler, right? Y of the monkey starts out at d, doesn't the monkey? Or it starts out at h. All right, so the monkey is at h. That's his initial. He has no initial y velocity, right? It's not falling at the beginning. It starts out at 0. So it's also plus 1/2 negative 9.8 the same time, d squared over v naught squared cosine squared theta naught. Okay? So the big question is, what does, what is required, I don't know what that says, for y bullet to equal y monkey? So we set them equal to each other and say, what does this tell us? Well, you can see what's going to happen. You set them equal to each other, and these two terms are the same. Those are going away. Right? So we get that v naught sine theta naught over v naught cosine theta naught, and there must be a d there. Yeah, d. D has to basically be equal to h. Right? Oh, the v naughts go away. What's sine theta over cosine theta? Is tangent theta naught. And that's equal to h over d. Not h and d, h over d. So for these things to hit, this has to be true. But what was the initial condition? Oh, that tangent of theta is opposite over adjacent. Tangent theta is h over d. All right? So this is basically saying, mathematically, that if you initially aim right at the monkey and you shoot the bullet, you'll still hit the monkey because the bullet will fall in the same amount that the monkey will fall. And you'll still hit it. And that happened mathematically when we realized these terms are the same. So in terms of the relative height of the two objects, the fact that they're falling doesn't matter because it cancels out. See? Should we prove it? Do we want to do this? Gun, monkey? Yes. Well, we're going to. I don't care if you don't want to. We're going to. Okay, so here's how this works. This is the gun. I have it preloaded with a bullet. There's a bullet, there's like a Teflon plug in there. And when I blow really hard on this tube, this very sanitary tube from like 100 years ago, it's going to shoot out, and it's actually going to break the circuit right here. This little thingy comes open, and that breaks a circuit that stops an electromagnet, and the monkey is held up by an electromagnet. Okay? So that way the monkey drops. It doesn't really hear a sound and freak out. We break a circuit, which breaks the current, which makes the monkey drop. Okay, so now we got to get the monkey out. Now this year we tried to do something a little bit special. Okay, this year we used to have this monkey that we used here, but this year we decided, you guys are paying a lot of tuition, we actually have a real monkey. We're going to do this with a live monkey. Hold on, let me get it out here. I'm fucking with it. It's not a live monkey. It's a fake monkey. We wouldn't do it with a live monkey. I'd never get away with it. I think I forgot to turn the current all the way up. There we go. Okay, so the monkey has a bolt in his head, and there's the electromagnet up there, right? And he's going to stick up there like this. Right, okay. Okay, now we don't have to do it this way. So if you've ever seen this before, most people shoot it like a meter because they want to be guaranteed a hit, right? Now, would you rather be guaranteed a hit, or would you rather see 10 meters and it might not hit? 10 meters, exactly. If you say that short distance, then you need to take a different class. This class is for people that want to do the full 10 meters. Okay. So all I'm going to do now is catch my breath enough, and we're going to shoot, and you just got to watch and see if it hits the monkey. Set your faces for stunned. Okay, here we go. Ready? Can you blow this? I'm tired. No, I got it. Sorry. I'm running around too much. Okay. Nailed the monkey right in the chest. Perfect monkey. Poor monkey. Oh my God. Okay. Sad, sad. Ping pong balls bouncing. It's just pathetic what happened to that monkey. Okay. So that's really all of the... are we in the second half? Yeah. That's really all of the projectiles we're going to do. Now we got one more thing to talk about. And we'll talk about it a little bit conceptually. It'll be fun. Don't worry. Lying. We're going to talk about the Galilean transformations. Okay. So when Galileo was 13, he started to notice some changes. Oh, no, wait, that's wrong. No, it's about motion in different reference frames. I was in the wrong class, sorry. Different reference frames. Okay, so for this, what we're going to do is focus. We're going to try to focus. See if we can focus. Too many toys, we can't focus. Okay. We're going to focus on where Hal is. Hal is just sitting there. And at first, he's not even going to move. Hal is just going to sit right there. You're seeing Hal over here. Okay, now we're going to put him over here. Trying to make it match my notes here. Oh, I also have to turn this off or the magnet melts. Hold on. Oh, okay. Okay, let's see. So we're going to think about how do we transfer from one frame of reference to another. Okay, that's all we're going to think about. And then we'll do a quick problem on how this works. So what you got to realize is every object can, in principle, have its own Cartesian reference frame, its own Cartesian coordinate system, or with a center on itself. Right? This is a very me-focused kind of a thing. This is my coordinate system. It always follows me around. I don't care about your coordinate system. So I'm going to be a Cartesian coordinate system right here. And we're going to do x and y like along the floor. So we're not thinking about z. Now x and y means like this. So now you're looking down. Right? So here's the bench here. Right? That's the big wooden thing there. And relative to me, here's Hal over here. Right? And I'm standing, say, about right here. So this is the JH coordinate system. Okay? And that's Hal over there. We'll call that, I don't know, I forgot. Hal, yeah. Okay, so my coordinate system looks like this. Here is y, and here is x. And everything that you would describe in my coordinate system, you describe relative to where I'm standing, right here. I mean, I'll try to stay in one place, right? So this is the origin. It'd be a vector going like that. So we also have Hal as an object. I don't want to draw him too weird, right? Hal is an object. So we want to describe Hal in two reference systems, okay? So we need mine here, and we need yours in the white jacket. What are your initials? MD. Okay, so MD. Is that funny? I don't know. Okay. Because you're pre-meds, is that why it was fine? Oh, okay. It's like, I don't get it. Okay. So here's MD, right? So MD has her own coordinate system, right? So I'll draw it dotted like that, because mine is the solid one, and yours is the sketchy dotted one like that. Okay, so there you go. So there is her Cartesian coordinate system, right? So I want both me and MD to think about where is Hal. Like, which direction is Hal, where's Hal sitting? So now we're going to draw 3 vectors, okay? We're going to say, first of all, where is Hal in my coordinate system? Okay, so we're going to say R, and I'm going to write the notation looks like this. Hal, which is the object, dash JH. And that is the position of Hal in the JH frame, right? So that vector looks like this. Oh, it's a position vector. It starts at the origin, and you draw it up to there. That's R, Hal, JH, right? But then MD, now this is awkward because I don't actually know your name and I'm calling you MD, says, no, it's not there. It's like in the negative x direction, or the negative y direction. So MD would say, no, it's here, like that. That's R of Hal. The object goes first and the coordinate system goes second, right? R, Hal. Oh, wait a minute, I'm sorry. Wait, hold on. No, let's not look at that one yet. Oh, I got this all screwed up. I forgot how to do these problems. Hold on, what am I saying here? Sorry, Hal and position coordinates, blah, 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 blah. I'm going to add this plus this. I think I just want to describe all of them. Yeah, no, that was okay. Redraw that, sorry. Okay, so this is Hal in MD's position. So the position of Hal in MD's frame, right? Yes, okay, I drew the right one. Okay, sorry. R of Hal in MD's frame. Right, okay. So the third vector is where is MD relative to me? Right? Our coordinate systems are related by this vector. Like that. R of MD in my frame. Right? R of MD in JH. Right? Position of MD in the JH frame. So you draw those 3 vectors. And there's no arbitrariness about which way they go. They're all as clear as they can be. The object of Hal in JH's frame must come from the origin of JH and go to Hal. Right? Hal in MD's frame must start at the origin of MD's frame and go to Hal. And then MD in my frame must start at the origin of my frame and go to MD. Right? That's how you would draw those 3 critical vectors. Okay? And now it looks like, if you look at it, it kind of looks like a vector sum, doesn't it? It looks like we've added the top 2 to get the bottom one. Looks like a vector sum. It looks like we've said R, let's see, what does it look like? Hal, JH. Oh yeah, no, that's right. It looks like, right, R of Hal and M, got the order different. Yeah, of Hal in MD's frame, right? That's that first, that vector. Shit, okay. Let me just not look at my notes. Let's just do this. It looks like a vector sum, doesn't it? It looks like R of MD in my frame plus R of Hal in MD's frame, right, equals R of Hal in JH's frame. Yeah. Yes, that's what it looks like. Right. Sorry, that took me 4 minutes. That would I expect you to figure out faster than what it took me. Sorry. So that's the sum. That looks like a sum. Okay. So now what I'm trying to get to is to think about how you can always convert. Okay. So how to convert. So say this is an example where we knew the position of Hal in MD's frame, and we know R relative, but the question is, what is Hal in my frame, right? So you know, say you know R, say you want, you've got to write what you want. Want Hal in my frame, the way I drew it, okay? That's what you want. You want Hal in my frame. Forget everything I've said. Just write it down, and it'll make sense later. You want Hal in my frame. What you do is you say, okay, what I want is R of Hal. The object goes first and the frame goes second. Okay? So what I'm trying to show you awkwardly here is you don't have to draw any vectors. You don't have to draw any diagrams. You just have to follow a rule. Okay? Here's the rule that I was awkwardly trying to get to. Is first you write this one. You say R, the position vector of Hal in something, plus the R of the something in my frame. That's all you write. And what is the something? The something is the other frame. Right? So we say, oh, Hal in MD, MD in JH. Right? That's how you'll always get it right. Okay? If you try to do it in your head, you'll usually get it right because you're really smart. But sometimes you'll screw it up. Okay? Because there's negative signs involved and it's two-dimensional. It's easy to screw up. But this is a general rule. If you ever want the position, like in a problem, it says, well, what is the position of Hal in this frame? And you weren't given that. You just set it up like this. You say, well, if I want this and this, I have this and something in this. And now go back and look at the problem and you realize, oh, wait, I had Hal in this frame. And then you realize you had that. And then you can still do it. Okay? So all that was just to get to that simple rule. That's all I was really trying to get to. Right? So A, B, A, something, something, B. That's all that is. So now let's look at what we can do with it. All right, here we go. Let's do something with that. Oh, I forgot to say, if y'all were confused by that one board, if you 0.4 was negative, that fixes everything. There you go. If you don't know what I'm talking about, don't worry about it. But if you notice that, that fixed it. Oh, everybody flips back, yes. Okay, so now to make this interesting is we take the derivative with respect to time. Right? So we determined that the position of Hal in my frame is the position of Hal in MD's frame plus the position of MD in my frame. So just take a derivative. Right? Then the velocity of Hal in my frame is the velocity of Hal in MD's frame plus the velocity of MD in my frame. It's the exact same rule. The exact same pattern is also true. Because all we do is take a derivative. What's the derivative? If Hal is moving in my frame, the derivative would be the velocity. If Hal's moving in her frame, the velocity. If she's moving in mine, the velocity. So you take the derivative of all three, it still has to be true. Right? So this really is the Galilean transformation, the idea that velocities transform like this. Okay? I was showing it to you first in position because that was what was going to make it really clear. So it didn't really happen. Okay? Usually you go straight to this. Okay? It also works for acceleration, but that gets really complicated. So you're just going to have to deal with it in terms of velocity. So what is he talking about? How do we use this? Let's do a quick problem with this. Okay? Or let me see what questions have come up. I may just ignore them because I was all confused. Huh? Yeah. That's right. Okay, none of these are about my class. Okay. So the kind of a problem you'll do here. So let's write out a whole problem. This is so important here. I'm going to use this board. Oh, no. Yeah. Let's see. The kinds of problems you do are almost always about boats crossing a river or things flying in the air. Okay? So this is a case where you got to be able to read that problem and see the context to figure it out. Okay? So when a boat moves in water, okay, or an airplane in the air, I won't write that part. It moves in the water's reference frame. This is how we use this for problems. Or there are other things we can do. Okay? So let's look at just a quick example of how this works. So a boat travels 3 meters per second across a river moving at 2 meters per second. So let's think about that real quick. We have a river, and it's moving. The V of the water is 2 meters per second. Pretty fast. And you have a boat here that thinks it's moving at 3 meters per second. Now, just your intuition tells you what's going to happen, right? The boat thinks it's puttering along at 3 meters per second, but you're watching it, and you know what it's really doing. It's going like this, right? If you start here, and you're standing here, and your friend is here, and they try to go straight across the river, they're really going to drift because they're in the frame of the water. So hopefully, intuition-wise, you kind of see what I mean there. Okay? So now what we're going to do is apply all those vector rules that we just did and see if it makes sense. So let's draw it again here with a little bit of room. Here. So here it is. Here's the boat. So this vector, that is the boat, how it thinks it's moving. The boat always moves in the water's frame. So this is V of the boat in the water. Right? And then what else do we know? We know, let's see, the water is moving this way. Well, that's V of the water, but in what frame? Whose frame is that? So this problem might ask, how far does the boat drift across before, by the time, how far does the boat drift this way to go across? And then you got to read the problem and figure out, there's one more frame. Whose frame is it? It's the person standing over here, confused in physics class. Right? Like, what the hell is he talking about? It's the ground. Okay, I'll call it the ground frame. We'll call it the ground. Let's call it what I did in my notes. The land frame. This is the land frame. So in most problems, there'll be a third frame. They won't name it, but it's just you. It's just watching. Sometimes it's called the lab frame or the building frame. So this is the velocity of the water in the lab frame. When somebody tells you how fast a river is rushing, what do you assume they mean with respect to? Somebody standing there watching the water rushing. So there's that and there's that. So you could say, well, I want then, if I got to answer this question, to answer the question that I didn't state, you need what? You need the velocity of the boat in the land frame. Because you want to know how is it moving. If you have these kinematics, and you can figure out it takes this long to cross, and in that time it drifts this long, right? So somehow you got to put these three things together. So how do you do it? You say, I want this. I want V, B, L. I want the velocity of the boat in the land frame. Don't even going to look yet. Don't even think. Don't look at the problem. Don't read anything. Just write V, B dash something plus V something dash B. Right? I'm sorry, dash L. Sorry. Right? That's how the rule works. B to something, something to L. And you say, do I know these? Oh, it's the water. The water boat in the water frame plus the water in the land frame. So it turns out they gave me exactly what I needed, right, to solve the problem. Okay? And this is how all the little components will go together. For example, in this problem, the question might have been, how fast is it moving in the land frame? Like, how fast is this boat actually going? And of course, by actually, we mean the land frame. There's really nothing universally important about the land frame, but that's what we usually mean in a problem. And you say, okay, well, I could write that. I could even write that in Cartesian coordinates. I could even write that out in Cartesian, because I could say, okay, it's this plus this. Let's practice our vector notation here. If we say this is y, and this is x, and this is all Cartesian, then what is the horizontal component? So they're already broken into components here, right? So your horizontal is strictly from the water and the land frame, the way I drew it. And it was water and land frame 2 meters per second. So it'd be 2 meters per second I hat. Oh, those are rearing their ugly heads again, right? I hat. And then what is its y component? Well, that's entirely coming from the boat. What the boat thinks it's moving with, what the boat is moving with respect to the water. All right, so that's up. I think I called that 3. Right, plus 3 meters per second j hat. Just means the x component and the y component. And now I promised you that at the end the problem would say, well, what is, or convert back to polar. And this is the case. We have to convert back to polar because they want to know how fast is it moving. They want the total velocity. They want the speed. Right? They want the magnitude of the velocity. So if we have that, then we say the magnitude of the boat in the land frame, how fast it's going, independent of axes, just how fast it's going. Oh, it's Pythagorean. 2 squared plus 3 squared, whatever that is. The square root of 13 meters per second. Okay? So this is a case where it was kind of straightforward. Without going through this formality, you might have said, well, it sounds like a right triangle, doesn't it? Because we have one component here and one component there, so it must be that. That's really all you had to do. The boat, the water, together they make this. But when problems start moving in 3 dimensions and things aren't perpendicular, it can get a little more confusing, and this is formally how you get it. Okay? Let's see. I think for this last part, I'm just going to blow your mind with it, and then I'll do a problem on like the video channel or something like that. What is the difference between the vector sum equation and the converted equation? I think this was too long ago. Yeah, these are too far back. Sorry. I missed all these. Let me just show you one thing, and we'll all think about what we think is the answer, and then we'll just go. Because this is a weird, counterintuitive thing about relative motion and angles. Okay? Yeah, somebody I think asked, what's the difference between that equation and just a vector sum? Nothing. That's the point. It's all this really is a vector sum. That's really all the relative motion equation is. Let's imagine here we have a projectile launched from a moving object. So if I wanted to combine things, motion problems involving moving reference frames, the difficult thing we might do is combine a projectile with a moving reference frame. And that would be the hard problem. And there's one in your homework. Right? So let's look real quick. So we have projectile from moving reference frame. Oh my God. So you have a truck here. And you have this cannon at some angle 45 degrees. Right? And you have a bullet and it comes out like that. V0. Boom. 45 degrees. I'll make it clear. I was 45 degrees. But the truck is moving at V. Some V also. Right? And the question is, well, there's a lot of questions we could ask. What angle is the bullet launched in the ground frame? What angle? So the 45 is in the truck frame, right? So this is the velocity vector of the bullet in the truck frame. The thing's mounted at 45 degrees. It's moving forward. It shoots it at 45 degrees. Right? This is the velocity of the truck in the ground frame, moving forward. So before we do it, let's test our intuition. We're going to do a 3 count, and you're going to say if you think it's higher angle or lower angle. Higher angle or lower angle. You ready? Say higher or lower. 1, 2, 3. Everybody said higher? I heard a lot of higher. Let's do the thing. What is the velocity of the bullet in the ground frame? Oh, this is the velocity of the bullet in some frame plus the velocity of something in the ground frame. And the thing in between is the truck. Right? So let's see. Let's now just do our vector sum. What's the velocity of the bullet in the truck frame? It's there. What's the velocity of the truck in the ground frame? It's there. It's lower. Right? The thing actually shoots at a lower angle because the truck is moving forward. Yeah, I know. It's weird. I don't know why we always think it's higher. I think it's because we think of the wind blowing it up, or we think of the truck accelerating under it, which it doesn't do. Right? But it's actually lower. And it actually makes sense. If you took this velocity vector and just added some of this, what? The net is lower. It's got to be lower. So the angle does something kind of counterintuitive. And then once you set that up, then you know how fast it's moving, and you could do the kinematics in the ground frame. It's just a mass launched at this new velocity, a new magnitude and a new angle. And then you just forget about the truck. So that's the one about beer bike, or about the water balloon fight at beer bike. So good luck with that one. All right.